Step Talk Education. We are still proceeding with organic chemistry and still trying to analyze what isomerism is. We started by looking at structural isomerism, discussed all the three modes of structure isomerism. That was chain isomerism, chain isomerism, position, and then functional group. Now we are looking at the second case of isomerism, which is called stereoisomerism. Now, this stereoisomerism is the existence of different compounds. Is there the existence of different compounds with the same molecular formula and the functional group. Same molecular formula and functional group. But differ in the arrangement of atoms in space. We can call it differ in the arrangement of atoms in space, or somebody can say differ in the arrangement of carbon atoms in space, or spatial arrangement of atoms. That is the meaning of stereoisomerism. Now, funny enough, this stereoisomerism predominantly exists in alkenes. Predominantly exists in alkenes. Why does it predominantly exist in alkenes and not alkanes? The reason is, let me now compare alkanes and alkenes. Now, these alkenes are preferably alkanes formed by sp3 hybridization, and therefore they only form sigma bonds. And sigma bonds are formed as a result of head-on overlap of atomic orbitals to obtain molecular orbitals forming alkanes. And once they can overlap overhead, then they form very strong bonds, very strong to break. Strong to break. They are really very strong to break, but allow free rotation. They allow free rotation, or we can call it delocalization. They allow free delocalization of atoms in space. Now, when you look at alkenes, alkenes are formed by sp2 hybridization. They are formed by sp2 hybridization. Now, they form both sigma and pi bonds. Form both sigma and pi bonds. Now, these sigma are very hard to break and therefore allow free delocalization or free rotation of electrons around this double bond. Now, these pi bonds are very weak to break. Only that they do not allow delocalization of atoms around their double bond. And therefore, this gives rise to the stereoisomerism. That's why these alkanes do not exhibit stereoisomerism, but alkanes really do exhibit stereoisomerism because of the existence of the pi bonds, although they still have also sigma, but this gives them an advantage of exhibiting stereoisomerism. Now, this gives rise, the phenomenon of free rotation gives rise to what we call the cis isomers and then the trans isomers. The cis isomers and then the trans isomers. Now, let us first proceed and discuss about cis isomers. Now, these cis isomers are types of isomers under stereoisomerism, whereby same groups are on same side around double bond, but on different carbon atoms. They are on same side. This same side is very important. They're on same side around the double bond, but on different carbon atoms. Take an example. If I had carbon atoms like this around the double bond, if I'm having X here, then I should also have X here. Then maybe I can say this is hydrogen, this is also hydrogen. These are same or identical groups. They are on same side, but different carbon atoms. These are also same groups, same side, but different carbon atoms. This is a cis isomer. But compare it with this one. Compare it with that one. Now, here, same groups are also still on the same side. Because when you look at, if we can divide this alkene by this, that is also still same side. Same side, same side. But this is same carbon atom, same carbon atom. So therefore, this is not a cis isomer. It is really not a cis isomer because it does not conform to the generalization that cis isomers should have. So this is a cis isomer because it has got the same groups around the double bond but on different carbon atoms, while the other one is violating the rule. Those are cis isomers. Now, we can go to trans isomers. Now, these trans isomers, just like we say the cis have same groups on same side, but different carbon atoms. The trans also have same groups on different sides and different carbon atoms. Different carbon atoms around the double bond. Around the double bond. So we are saying they have different groups Now, take an example. We could have the double bond between the two carbon atoms these are same groups on different carbon atoms and different sides. Now, when you look at this methyl and that methyl, they are same groups on different sides. The other side, when you divide this into two, the other one is the left-hand side and this is the right-hand side. So they are same groups on different sides and different carbon atoms entirely, but of course revolving around the double bond. Now, here we can also still have hydrogen here. We also have another hydrogen here. So now this one qualifies to be called a trans isomer. And by IUPAC name, we can name this one as trans but2-in. That is trans but2-in. Now, we would compare it with the cis, whereby this would be a methyl, okay? This would also definitely be another methyl. This would be a hydrogen, and this would be also hydrogen. So when we look at this group, this structure and that structure, this one has same groups on different carbons and different sides, but revolving around the double bond and different carbon atoms. These are same groups, different carbon atoms, and the same side. Therefore, this conforms to the cis isomer. So therefore, we call this one as the cis but2-in. That's the type of isomers. Now, in brief, stereoisomerism has got two types. The types of stereoisomerism. There are basically two types, and number one is geometric isomerism, and then number two we have optical isomerism. Now, this geometric has already been discussed about because it is the one which leads to the rise of the cis isomer and the trans isomer. Because it is just about the existence of different compounds with the same molecular formula, same functional group, but differ in the arrangement of carbon atoms around the double bond. So the different arrangement of groups, of different groups around the double bond of carbon atoms gives rise to the cis and the trans. And then the cis and trans have already been discussed above. So that is geometric isomerism. Then this word optical isomerism, optical simply means light. It simply means light. And it is all about a compound forming a mirror image. Take an example, if we do have this as our mirror, and you put a cup here, let us see here, this side it would appear like that. So this C is a mirror image of this one. The two are not really superimposable. Now, when you look at, if this is still our mirror, and we have our compound here like this. That's our compound, and we have to have a mirror here. Then it will change and become this, that is letter C in the middle. Then